Okay, so Coulomb's law is what we want to talk about next. And we know that if you have charged particles, they're either going to attract or they're going to repel. So we know there has to be some kind of force involved. Everybody agree with me there? And so it's an attractive force or it's a repulsive force. And we need to be able to figure out the formula that relates the charges with the force. So Mr. Coulomb says that 2-point charges exert a force on one another. It's directly proportional to the product of the magnitudes of the charges and inversely proportional to the square. So if you look at that, here's what he's really saying. He's saying that F is proportional to Q1 times Q2, where those are charges on objects 1 and 2, and inversely proportional to the square of their distance of separation, how far apart they are squared. Okay? Well, that makes sense because the farther they are apart, the less force they're going to have on each other. The bigger the charges, the more force they're going to have on each other. The closer they are, the larger the force. What's the matter? Is proportional to? Okay. So this sign right here, this little symbol that we were asking about, that's the alpha. Means is proportional to. Now, that's all well and good, but I can't do any math with simply is proportional to. I need to change that to an equal sign. So to do that, I have to introduce something called a constant of proportionality. In this case, my constant of proportionality, and that's just a value that always makes it be an equation as opposed to a relationship. Proportionality. I'm going to use a K for this particular problem, or for this particular law, and my K is equal to 9 times 10 to the 9th Newton meter squared over Coulomb squared. Coulombs squared. Too much chemistry in my life. There we go. All right. Do you remember this equation right here from last semester? Do you see the similarities between this and this? Gravity is only attractive, would you agree? This force can be attractive and repulsive. This is a constant of proportionality, and we used, what, 6.67 times 10 to the negative 11th? Do you remember that? So we're doing the same thing here mathematically. We're looking at charges instead of masses, but we're still looking at how far apart they are, and we're still looking for a constant of proportionality. And so this is the value that you're going to use for Coulomb's law. Okay? Pardon? Okay, so then my relationship becomes K, Q1, Q2 over R squared. So I know what K is. Q1 is the charge on object 1 in coulombs. And it's expressed in coulombs. Q2 is the charge on object 2. Expressed in coulombs. And R is the distance of separation, and it needs to be in meters. All right. Everybody okay with that? All right. All right, so let's look at that. You have 3 charges. This one is negative, negative, and positive. I want to know what's happening. What is the force on 3? How do I know? Because it says what is the resultant force on the 3rd charge. All right. So what is 1 doing to 3? Is it attracting it or repelling it? Excellent. So 1 is pushing 3 in that direction. Everybody all right with that? What is 2 doing to 3? So 2 is pulling 3 in that direction. Bless you. Is everybody okay with that? The hardest thing about this whole concept is getting these directions correct, because some students want to tell me that direction. I don't want that direction because that tells me what 3 is doing to 1. The question is asking me what is happening to 3. Do you see the difference there? Okay. If I put the red arrow there, that's telling me what 3 is doing to 1, but the question does not ask me that. So be very careful about your vector directions. You know how to do it. It's not a new concept for you. You can do it. So if I find the force of 1 on 3 and the force of 2 on 3, does it make sense that I'm going to add them to get the net force on 3? Is everybody all right with that? Because they're both in the same direction. 1 is pushing 3 to the right. 2 is pulling 3 to the right. Does that make sense? Candace? Make sense? All right. So now I'm going to try to find my forces. So the force of 1 on 3 is going to be K. And yes, you need to write it out. Q1 is negative 8 microcoulombs. Leave your negative signs out of here. Micro is 10 to the minus 6. Q3 is 4 times 10 to the minus 6 coulombs. And they are separated by 6 centimeters, or 0.06 meters. And I got to square that little rascal. Now, the reason I told you to leave the signs out of your work is because the signs got dealt with when I talked about attraction and repulsion. If you put them in here, it makes you confused and nuts, because typically I say a negative force is to the left. Here, a negative force would indicate attraction. So don't do that. Leave them out. It'll make your life a lot easier. Okay, so then you crank up your calculator, and you do the top 9 times 10 to the 9th times 8 times 10 to the minus 6 times 4 times 10 to the minus 6 and divide by 0.06. And I don't think I can do this in my head, but 32 times 8 is 288 divided by 36. I don't think I can do that in my head. Would someone do that for us and tell us what they get for that force? Has someone already done it? Rod, do you already have it? Nope. Because micro means 10 to the minus 6. Good question. What did you get? 80? All right. And force of 1 on 3, 1 is pushing 3 in that direction. Now I want to do the force of 2 on 3. So I'll do 9 times 10 to the 9th. Times Q2, which is 12 microcoulombs. And micro is 10 to the minus 6, so that's where I'm getting that minus 6 from. And times 10 to the minus 6 for my Q3. And they're still separated by 0.06 meters. And I got to square that. So I think that's going to be 120, but somebody check. Yes, Madam Morgan Kelsey. All right, so I have 120 newtons, and it's to the right. So the net force on 3 is going to be 80 newtons to the right, 120 newtons to the right, so I can simply add those and get 200 newtons for the magnitude, and the direction would be to the right. Okay, so here they give us one where it's not all straight lines. We have to start dealing with the fact that we have a triangle. And while I don't want to solve it today, I want to kind of talk through the forces. I'm looking at Q3, which is this one right here. So 1 is up here. 1 is pulling 3 in that direction. 2 is pushing 3 in that direction. So you wind up with, remember the little XY chart? And you resolve this into a component and a component. Do you remember that? So that's why I don't really want to deal with it today, but it's not that hard. We know how to do it. Okay? So we'll spend some time working on that. It just won't be today. All right. So let's move on to another one after I get through all the PowerPoint. All right, so you can see that's a whole lot of work. And that's okay. We'll get there. We're just not, there's no need to rush to it and do it today. All right, so I'm going to stop there because I don't want to talk about the electric field with you yet. That was pretty simple.